were considering regular expressions. A regular expression starts with phi, epsilon or letters of sigma. A is a letter belonging to sigma, and then it uses the operation of plus, dot, star a finite number of times, and you get a regular expression. We were considering some examples of regular expression. For example, 0 plus 1 star denotes the set of all strings over 0 and 1 are all binary strings. A string of the form a plus b star a plus b star. This is a regular expression. It denotes the set of strings which have at least one consecutive AA. Any string of A's and B's followed by a AA and any string of A's and B's. So, the language consists of all strings having at least one pair of consecutive A's, and A plus B star AA plus BB A plus B star. This denotes the set of strings which have at least one consecutive pair of A's or one consecutive pair of B's. An expression of this form AB star AA plus BB, this represents the set of strings which either end with a pair of A's or end with a pair of B's. Any string of A's and B's you can have, but it should end with a pair of A's or pair of B's. Now, look at this expression 0 plus 0 1 star. Consider this expression 0 plus 0 1 star. What does the set represented by this expression? What is the set represented by this regular expression? Now, you see that you can have any number of zeros, because 0 0 0 you can have, or you can have 0 1 0 1 a number of times, again any number of zeros you can have 0 1 and so on. But you see that after a 1 occurs, either you will get a 0 or you will get a 0 1. So, when you get a 1, see 0 1 occurs, this is a sequence followed by zeros and 0 1s. The set of strings represented by this regular expression consists of a sequence of zeros and 0 1s. So, when you have 0 1, next it will be followed either by a 0 1 or it can be followed by many zeros. Whatever it is, you can see that you will not get two consecutive ones. After a 1 occurs, it will occur because you get a 0 1, and after that either you will get a 0 or a 0 1. So, you will not get two consecutive ones. So, this expression represents a set of zeros and strings over 0 and 1 or binary strings where you cannot have two consecutive ones. And you must also note that it begins with a 0. It can end with a 1 or a 0, but it begins with always with a 0. Now, if you allow the possibility that initially you can have a 1, again you cannot have two consecutive ones, but the string may begin with a 1. If you allow for that possibility, then you have 1 plus epsilon 0 plus 0 1 star. So, this denotes that either you begin with a 1, if you take epsilon, that means nothing is taken from this portion. So, it can begin with a 0. The string can begin with a 0 or with a 1, and then it will be followed by some other things, but the main thing is you will not have two consecutive ones. Now, if you want to represent the set of decimals, we have already seen how to represent the set of Fortran identifiers. if you want to represent first the set of integers, let me denote by digit 1, digit 0, digit minus 0, digit hyphen 0. This is 1 plus 2 plus 9, and digit is 0 plus 1 plus 9. So, integers can be represented by digit hyphen 0 followed by digit star, or in essence the regular expression, if the alphabet is 0 to 9, it will be 1 plus 2 plus 9 followed by 0 plus 1 plus 9 star. If you want to represent a decimal, it will be an integer followed by a dot followed by a sequence of digits. So, it will be integer dot digit star. So, we assume that you are representing integers greater than 1. So, first portion you have, if you can allow for 0 also, 0 something like that. In that case, you will have integer plus 0 dot digit star. Please note that you also allow something like in this expression, you will also have something plus like this will also be in the language. So, like this you can express certain things using regular expressions. Suppose you want to represent the set of strings over A and B of length divisible by length, which is a multiple of 3. The regular expression for that will be, you can have a plus B or you can have a plus B, the length will be 3. This allows all strings. This regular expression represents the set of all strings over A B which are multiple of 3. Epsilon is also allowed. When you have this star, epsilon is also allowed here, and similarly you can see that in this regular expression epsilon will be in the language. Epsilon will not be in the language represented by this because it has to end with 2 A's or 2 B's. The minimum length string is AA or BB in this case. So, having defined this, we have to see that we have seen that NFSA with epsilon moves and NFSA, DFSA and regular expressions. So, today these things we have already considered. Today we shall consider this, how to get a NFSA with epsilon moves from a regular expression. Now, given a regular expression, how to construct a non-deterministic FSA with epsilon moves. This is what we will see now. How do you define a regular expression? You start from the empty set epsilon and symbols of sigma and perform the operation of union, concatenation and star a finite number of times. Now, the definition of regular expression is like this. Okay, I will rewrite the expression, though we have considered it in the last class. Phi is a regular expression denoting the empty set. Now, how can you draw a diagram non-deterministic FSA with epsilon moves for this? You can have a diagram like this, Q naught, QF, without any arc between them. What does this accept? This diagram, there is no arc there, it accepts the empty set, no string will be accepted, alright. This is the state diagram of a machine which accepts the empty set. Then epsilon is a regular expression denoting a set having only epsilon. Epsilon is a regular expression which denotes a regular set having only one string, and that one string is the empty string epsilon. Okay. How can you represent it by a FSA? There is only one state which is the initial state and the final state. When will epsilon be accepted? If the initial state is a final state, epsilon will be accepted. There are no more arcs, no transitions, so no other string will be accepted. Okay. Then A is a regular expression denoting the set containing just one string which is A. For each symbol in sigma, A is a regular expression which denotes a set having just one string which is A. How can you draw a diagram for this state diagram? You can have something like this, Q naught A QF. So, A alone will be accepted. Then what was the definition? If R1 and R2 are regular expressions denoting L1 and L2 respectively, R1 plus R2 is a regular expression which denotes L1 union L2. R1 R2 denotes a regular expression which denotes the concatenation of L1 and L2. R1 star is a regular expression which denotes L1 star. This we have seen. So, this is something like a basis class. You start with the empty set epsilon and symbols A. Then you use the operation of star plus concatenation a finite number of times and you get a regular expression. For example, if you look at this 0 plus 0 1 star, this is a regular expression. 0 and 1 are symbols. So, first you are concatenating 0 1, then you are using union, then you are using star. So, we do not write this as usually we do not write it as, this is what we mean 0, this is concatenation is performed first, then this union, then the star, right. Now, we do not write like this, we usually write like this because among these three operators star, dot, plus, this has the highest precedence. This has highest precedence, then concatenation, then union. Among these operators, this is the way you evaluate the expression. Okay. So, that is why because concatenation has higher precedence than the union, this parenthesis is omitted. Now, without loss of generality, you can assume that R1 is represented by a state diagram like this, which has a single state, it has a single initial state, single initial and single final state. Usually initial state is only one, but you can have several final states, right. That is what we have assumed. Now, without loss of generality, we can assume that there is only one initial state, that is always there. There is only one final state. There is only one final state and there is only one initial state. Similarly, R2 also can be represented by a diagram where you have a initial state and only one final state. How can we assume that? How are we justified in assuming this? Because we are considering a transition diagram or a state diagram with epsilon moves. Suppose there are say 3 final states, you make them all non-final, you introduce a new final state, make these non-final, and have epsilon transition to this final state, and there is no arc leaving from the final state, right. So, instead of having 3 final states, I can make them non-final and have only one final state, where from each final state an epsilon transition leads to the final state. Okay. The language accepted by such a transition diagram will not be affected by this, right. So, without loss of generality, you can assume that R1 is represented by a transition diagram or NFSA with epsilon moves, where there is a one initial state and only one final state. Similarly, R2 is also represented by a diagram with one initial state and one final state. Now, how do we go about defining R1 plus R2? So, this R1 is represented by M1 with an initial state and a final state, right. R2 is represented by another transition diagram with an initial state and final state. This is M2. So, R1 is represented by this, R2 is represented by this. How can you represent R1 plus R2 by a transition diagram or a NFSA with epsilon moves? I am using the word NFSA with epsilon moves and transition diagrams in an equivalent manner, state diagram or transition diagram. What you do is, you introduce a new initial state and remove them, these are no more initial states, right. introduce a new final state. These are no more final states. Right. Then add epsilon arcs here, add epsilon transitions here. Okay. So, this is a transition diagram or a non-deterministic FSA with epsilon moves. This has got a single initial state and a single final state. And what does it accept? If R1 accepts L1, R2 accepts L2, this accepts L1 union L2. Why? How do you define L1 union L2? L1 union L2 is X, X belongs to L1 or X belongs to L2, right. So, any string accepted by L1, you will go from here to here through a path. For M1, this is the initial state and this is the final state. So, if a string is accepted by M1 or if a string is in L1, it will be accepted by M1. So, that string will take you from this state to this final state, right, some x say. Then how will the same string be accepted by this diagram or this non-deterministic FSA with epsilon moves? Start from here, through an epsilon transition you go here, then reading x you go to this state, then through an epsilon transition you go to the final state. So, the string x will be accepted by this also if it belongs to L1. If it belongs to L2, it will be accepted by the NFSA M2 with epsilon moves. That is, suppose a string y is accepted, y is in L2, there will be a sequence of moves which takes you from this initial state to the final state here, because it is in L2 or it is accepted by M2, right. Now, how will this diagram accept that? Starting from here, go to this state through an epsilon transition, then after reading y you go to this state, then through an epsilon transition you reach here. So, the same string will be accepted. Okay. So, this diagram you can see that it is a non-deterministic FSA with epsilon moves and it will accept L1 union L2. Okay. Now, the concatenation of L1 and L2. Suppose L1 is accepted by a non-deterministic FSA with epsilon moves M1 with initial state and a final state, and L2 is accepted by M2 with initial state and final state like this. Now, you want to accept L1, L2. What is L1, L2? L1, L2 consists of strings of the form x, y, x belongs to L1 and y belongs to L2, right. Now, how can you get this from this diagram? You have a diagram where this will no longer be a final state and this will no longer be an initial state, and there is an epsilon transition from here to here. This is an NFSA with epsilon moves. What sort of strings will be accepted by this? If a string x can be accepted by M1 by going from this state to this state, and while going it reads the string x through the transitions, right. And a string y will be accepted by this machine by going from this state to this state, and while going from the initial state to the final state, it reads the string y including epsilon moves through the transitions, right. Now, what sorts of strings will be accepted by this diagram? This is the initial state. So, start from here and it reads a string of the form x, and then it makes an epsilon transition to this, then reads a string of the form y to reach a final state. So, the strings accepted by this transition diagram are the NFSA with epsilon moves will be of the form x y. In between you have an epsilon transition, right. So, this accepts L1 L2 or the set represented by R1 R2. Okay. Next we have L1 star. Okay. L1 is represented by R1 and it is represented by a NFSA with epsilon moves like this. Now, I want to have a NFSA with epsilon moves which will accept L1 star. What is L1 star? L1 star is L1 0 union L1, that is L1, right. And what sort of strings will be accepted by L1 star? See, it will have strings of the form xi1, xi2, xin. L1 star will consist of strings of the form xi1, xi2, xin, where each xi belongs to L1, and L1 0 represents just the empty string. So, empty string will also be there in the language. L1 star will contain the empty string also. Okay. So, the set of strings which are present in L1 star will be of the form xi1, xi2, xin, where each xij belongs to L1, right. Now, how will you modify this state diagram so that it accepts L1 star? You have one new initial state and one final state. This will be the initial state now and that will be the final state. These states will not be initial and final states. And you add epsilon transitions here. When we do this, what is the language accepted? Just after having done this, same as L1, nothing has changed. Instead of change, we have made a new initial state and a new final state, and starting from here you go here, any x you can read and go here. So, this just accepts L1 only. Now, you want to accept L1 star. So, from here to here you have an epsilon transition. So, what sort of strings will be accepted by this diagram? Starting from here you go here, you can read a xi1 and go here, go here again through epsilon transition, read xi2 here, go here, read xi3 here, go here, repeat this several times. After reading xin, you transit to the final state. So, strings of the form xi1, xi2, xin will be accepted. Is this okay or something is missing? Epsilon will not be accepted unless this accepts epsilon. L1 0 consists of epsilon, you have to accept epsilon alone. So, there should be one arc from the initial state to the final state with label epsilon. Okay. So, this diagram, this NFSA with epsilon moves will accept L1 star. Step by step construction you can use for a, let me take a simple expression. Zero plus 0 1 star. This represents a set which does not have two consecutive ones and it begins with a 0. Now, use the method zero will be accepted by something like this, or I will write here. Zero will be accepted by something like this, and 1 will be accepted by something like this. So, 0 1, in order to accept 0 1, this is not an initial state, this is not a final state. So, this will accept 0 1. Then I have 0 plus 0 1, another 0. For 0 you can have something like this. So, repeatedly use the construction. How will you accept 0 plus 0 1? Have a new initial state and a final state here. This will not be initial state, this will not be initial state, this will not be final state, this will not be final state. Then have an epsilon transition here, have an epsilon transition here, have an epsilon transition here. So, what is the language accepted by this? It will be 0 plus 0 1. How many states you are having? 1 2 3 4 5 6 7 8 states you are having. Now, you want to accept this star, right. So, use the construction, then you will add one more initial state, one more final state. This is the L1 portion, the whole portion, this is the L1 portion. You want to construct L1 star. So, you will not make this an initial state, this will not be made the final state, and you will add epsilon transitions here, an epsilon transition here, an epsilon transition here, and then an epsilon transition here. Systematically, if you construct using the construction we used, you will construct this. Then to get the deterministic diagram, deterministic, say what will you do? First of all, you have to remove the epsilon transitions and get an NFSA, then use the subset construction and get the deterministic. Number of states will be very large, the way you get number of states will be very large. So, this is just to prove that for any regular expression you can get an NFSA with epsilon moves. The construction which we used is to prove that given any regular expression you can construct an NFSA with epsilon moves which will accept the set represented by the regular expression, but that may be a very unwieldy way of doing it. For proof it is okay, but generally suppose you are given this, how will you construct the automaton? You will start from the scratch and say start with this initial state, then when you get a 0, any number of zeros you can read, because epsilon is accepted this will also be a final state. Okay. So, when you get a 1 you go to a state q1, right. Now, you cannot get 2 consecutive ones. So, if you get another 1 you will go to a dead state, but just this can be a final state. From this if you get a 0 you will go here, and from this if you get a 0 or a 1 you will go here. So, this will be the deterministic state diagram for this expression which has got only 3 states including the dead state. And it is easy, in this case it is very easy to draw this rather than this way of proceeding. The way we did this is to just prove, it is a proof by induction. Why it is a proof by induction? For the definition of regular expression we have used induction, means please remember that it is not necessary that it should be 1 to n like that. Underlying set is inductively defined. What is underlying set? The regular expression is inductively defined. Basis class is phi, epsilon and a are regular expressions. Then induction class is you use the operators plus dot, and dot is concatenation, star to build more and more regular expressions. To show that can be represented, that can be represented by NFSA with epsilon moves, basis class you show that phi, epsilon and each symbol can be accepted by a NFSA, and then induction portion is if R1 and R2 can be represented by M1 and M2, R1 plus R2 can be represented by a state diagram, R1 R2 can be represented by a state diagram, R1 star can be represented by a state diagram, and so on, right. Is it clear? So, in general you will not use this method for really constructing something, you will use a rather intuitive approach and try to construct the deterministic FSA straight away. In some cases the deterministic FSA may be a bit difficult, you can construct the non-deterministic FSA and then construct the deterministic FSA. So, if L1 and L2 are regular sets, then what are regular sets? Regular sets are sets accepted by FSA. They are also generated by type 3 grammars. Okay. So, from this argument we have shown that L1, L2, L1 union L2, L1 star are regular sets. Right? That is, the family of regular sets. Family of regular sets is the family contains all regular sets. Okay. So, the family of regular sets is closed under union concatenation and Kleene closure. So, because if L1 and L2 are regular sets, L1 union L2 is also a regular set. So, you say that the family of regular sets is closed under union, it is closed under concatenation, it is closed under star. Right. Now, what about intersection and complementation? If L1 and L2 are regular sets, what about L1 intersection L2 and L1? How do we define L1 bar? How do you define L1 bar? L1 bar is sigma star minus complement, set complement notation. Sigma star is a set of all strings over sigma. L1 represents a subset of that, right. So, the complement of L1 is the set of strings over sigma which are not in L1. Is that clear? Usual set theoretic notation. Now, if L1 is accepted by a state diagram like that with an initial state and some final state, it is a DFSA. So, I am not making one DFSA. If L1 is accepted by this diagram, how can you accept the complement? Just interchange the final and the non-final state. Have the same DFSA diagram, same deterministic final state diagram. Interchange the final and non-final states to get the DFSA for L1 bar. That is all. See, if a string is accepted by L1, it will take you from initial state to a final state. If X is accepted, it will be taken, it will take you from initial state to a final state. Now, you are making the final state and non-final state. So, X cannot be accepted. If a string Y takes you to a non-final state, that will not be accepted by L1, but you are making the non-final states as final states. So, Y will be accepted by the complement. Okay. Let me take a simple example. This example I have been repeating again and again. Q naught A Q1 Q2 A B B, and the dead state B A B A. What sort of strings will be accepted by this machine? A power n, a string of A's, A power n, B power m, nm greater than or equal to 1, or the language accepted consists of a sequence of A's followed by a sequence of B's. Epsilon is not accepted by this machine. Now, you want to accept the complement, then you should accept all strings over A and B which are not of this form. The complement should accept all strings which are not of this form. From this diagram, how will you get the diagram for the complement? Make this a non-final state and make every one other state final state. Okay. So, epsilon will be accepted, epsilon is not there here, epsilon will be accepted. A string of A's alone will not be in this language, but string of A's alone will be accepted by this diagram. Then A power n, B power n, string of A's followed by a string of B's will not be accepted by this diagram. But if a sequence of A's followed by a sequence of B's, then followed by something else, that will be accepted. A sequence of A's followed by a sequence of B's, then followed by something else will be accepted. So, whichever string which is not of this form will be accepted by this diagram. Okay. So, you are just interchanging the final and the non-final states to get the complement. Now, what about intersection? Intersection also it is closed. L1 intersection L2 is also a regular set. Suppose L1 is accepted by M1 equal to K1 sigma delta 1 Q naught 1 F1, and L2 is accepted by M2 equal to K2 sigma delta 2 say Q naught 2 F2. Sigma I am using the same. So, L1 is accepted by a finite state automaton like this, L2 is accepted by a finite state automaton. You can, without loss of generality, you can take them to be DFSA. Then L1 intersection L2 will be accepted by a machine M1 M. The set of states of M are ordered pairs. See, if Q is a state in K1, QP, states will be ordered pairs like this, Q belonging to K1, P belonging to K2. So, the set of states is the Cartesian product of K1 and K2. Input alphabet of course is sigma. You have to define delta the transition mapping. The initial state will be this pair, that is a pair consisting of the initial state of M1 and the initial state of M2, and final states again F1 cross F2, Cartesian product of F1 and F2. So, each state in this will be represented something like this, and we have to define delta. Okay. How do you define delta? Delta of QP comma A equal to RS, this RS, states are represented like this. When can you say like this? If delta 1 QA is equal to R and delta 2 PA is equal to S. Okay. So, what happens is, suppose a string A1, A2, A3, AN is accepted, starting from Q01, Q02, some states you will go through and finally end up with some QF1, QF2, right. In M, you will accept a string of this form through a sequence of states like this. Now, the first component takes care of the fact that it will be accepted by M1. The second component will take care of the fact that it will be accepted by M2. So, only when it is accepted by both M1 and M2, it will be accepted by the machine, and vice versa. If it, if it is accepted by this, it will be accepted by M1 and M2, and if it is accepted by M1 and M2 because of the first component and the second component, it will be accepted by M, right. So, this makes sure that both M1 and X. The construction is very simple, we can illustrate with an example. The example which we considered earlier. Strings over AB with two conditions, which is it begins with A and ends with B. A is not a subword. So, one diagram will be first condition Q naught A Q2 B B am I correct? String begins with a A and ends with a B. Okay. A, any A. No, this will have only one A, you can have several A's followed by a B. So, this will take you to a state no. A any number of A's, B and then okay. B. Then second condition is I am not drawing the dead state here, because any dead state if you go to, it will not lead to anything. So, I am omitting the dead state. What about the second condition? P naught A as long as you get a B, you can be here. If you get one A, you go here. Again, if you get a B, you can go here. A. If you get a you have to go to the dead state. But from here, if you get a, you go here. From here, if you get a B, here. From here, you cannot get a. If you get a B, you can go here. This will be the diagram. P1. I am not drawing the dead state here again. Dead state I am omitting, because anyway dead state will not lead to anything. So, for otherwise you can also have a dead state and draw the diagram completely, but for convenience sake I am omitting the dead state. Now, what are the final states here? This satisfies the condition that A is not a subword. So, this can be a final state, just AB can be accepted. This can be a final state, this can also be a final state, right. So, we get this automaton for satisfying both the conditions. We start initially with the pair Q naught P naught. Q naught is the initial state of this, P naught is the initial state for this. Now, what are the next states? Q naught A is Q1 and P naught A is P1. So, you get this pair here, and from Q naught you cannot get a B. So, this will go to a dead state. Then taking this pair Q1 P1, from Q1 if you get a you go to Q1, from P1 if you get a you go to P2, from Q1 if you get a B you go to Q2, from P1 if you get a B you go to P naught. Now, start with this pair Q1 P2. From Q1 if you get a you go to Q1, but from P2 you cannot get a. So, this will be really the empty state, it will go to the dead state. Then from Q1 if you get a B you go to Q2. From P2 if you get a B you go to P naught. With this pair on the left hand side, I mean starting with this pair Q2 P naught. From Q2 if you get a you go to Q1. From P naught if you get a you go to P1. So, you get the pair Q1 P1. For B, from Q2 if you get a B you go to Q2, from P naught if you get a B you go to P naught. So, we have considered all pairs, and let us draw the state diagram for this with the dead state. So, you will find that Q naught P naught is the initial state, and the other states are Q1 P1, Q1 P1, Q1 P2, and Q2 P naught, Q2 P naught, then there will be a dead state also for the deterministic diagram. So, marking the transitions from Q naught P naught, if you get a you go to Q1 P1, if you get a B you go to the dead state, then from the dead state if you get a B you go to the dead state. That may be denoted as phi 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 in another row if you want. Now, from Q1 P1 if you get a you go to Q1 P2, if you get a B you go to Q2 P naught. From Q1 P2 if you get a you go to the dead state, if you get a B you go to Q2 P naught. From Q2 P naught if you get a B you go to the Q2 P naught itself. If you get a you go to Q1 P1. So, this completes the state diagram of the machine. You can very easily see that A B will be accepted, A B will be accepted. So, any string okay. Now, what is the final state? The final state is such that the first component should be a final state of the first machine, the second component should be a final state of the second machine. The second machine all three are final state, in the first machine only Q2 is a final state. So, in this case only this is the final state. So, you can see that A B will be accepted, A B will be accepted, and if you get A it will go to the dead state. Any string after that will not be accepted, A occurs as a subword. From here again if you get a another subword it will go to the dead state. So, whenever you get 3 A's it will go to the dead state. So, the string will not be accepted, and reaching the final state you have to reach through a transition labeled B, and then afterwards you can get any number of B's you want. So, the string ends with a B. The string begins with a, the first symbol if it is a B, the string will be rejected by going to the dead state. So, this diagram you can draw straight away, or you can draw these two diagrams and then combine them using this method. So, this shows that if L1 and L2 are regular sets, L1 intersection L2 is also a regular set and can be accepted by a finite state automaton.